MS Shetty, the train, both of us were traveling from Chennai to Reddypalayam where Grasim had their plan, architect plan at that time. So he was talking about what made him write the book. Is he still alive?
He's strong and nearby.
Oh, he says something here? So he was telling me what made him write that book at that point of time. Okay. So if you had some introduction concrete, we'll do some more base stuff that is not generally seen in engineering textbooks. We'll do some research, state-of-the-art stuff, and if you listen to all the talks in the morning, everybody is complaining about concrete, right? And that'll happen. Why? When something is popular, you will complain. So that's part of what we deal with. If you are the owner of a very famous restaurant, you should be prepared for somebody to come and tell you your food is not good, right? If you expect everybody to come and say you are great, you're missing the point. But there's definitely things to improve. There are definitely ways in which we can improve. I was telling somebody this morning that the guest house I'm staying here, beautiful, nice guest house, but when it rains, water is coming inside. I don't know whether it was intentionally designed for water to come inside. They might have said, "Oh, have you seen or read about the falling water building that the famous architect Frank Lloyd Wright designed?" So this is Frank Lloyd Wright was a very famous architect, the one who designed Chandigarh along with Lake Corbusier. Frank Lloyd Wright designed this beautiful building because the owner of the building owned a lot of land through which a small river was flowing and there was a small waterfall. So he wanted the building to look like it's in sync with the nature. So he designed it in such a way that the building merges with it. It's called falling water. So it's like waterfall itself. Wonderful building. But Frank Lloyd Wright was an architect, not a structural engineer. So he designed 15-foot-long cantilevers of concrete. So you know what happens if you do 15-foot-long cantilevers of concrete, right? That's what happened. It started to sag, it started to crack, and then people complain, how come concrete is cracking? If you put a 15-foot-long cantilever, yes, it will crack. That's what it's supposed to do, you can't complain. So there are certain things. So if you look at some of the buildings in campus, some of the buildings that you see all over, when you see water coming in, and I was walking this morning in the campus, you see a lot of high-rise buildings very comfortably in sync with the vegetation around. You see creepers creeping on top of the concrete buildings. You see the roots of the trees living alongside concrete. Concrete is not designed to plant trees. So if that is what happens, and then your concrete fails, you can't complain about concrete, right? So I think there's a lot of things that we need to look at. There's a place, I built a building, I let it go. Concrete, so I keep telling, right? First 28 days, in India, if you have small babies, you have ceremonies in 28 days, right? Or 3 weeks, 4 weeks ceremonies. Concrete is like that. You have to treat it like a baby for the first 28 days. You have to treat it exactly like you treat a baby for the first 28 days. And then, it will treat you like an adult later on. Concrete goes through everything that a human being goes through. It grows, it ages, gets strength, deteriorates, falls. So, like you take medicines after a certain age to keep you alive, you need concrete also to take some medicines, you need maintenance. You need to go to yearly checkups. We all go to yearly doctor checkups, right? To check your blood pressure, at ECG. You need that for concrete also. So it's a comprehensive, and we'll talk about a lot of these things of microstructure where it all starts. I don't think I need it. You all can hear me, right?
Yes.
If you can hear me, I'll go without a mic. Okay, so this course is basically on concrete microstructure characterization. We'll do a bit of characterization, but I don't want you to overwhelm with characterization techniques when you don't have it with you. So this is like teaching an X-ray technician to take an X-ray without an X-ray. I don't want to do too much of that. I'll give you an introduction to many of those things so that when you see it, when you feel it, you know what that is and you can have the further knowledge. Okay? So we'll try to cover broad-based strategies of what concrete is, build on what you know already about concrete, and then add on top of it some of the new advancements that are happening, with an emphasis on, possibly I'll try my best, with an emphasis on Indian conditions, because that seems to be the flavor of the day. Okay, we'll try to do it with an emphasis on Indian conditions. Now, stop me whenever you have to ask a question. Stop me whenever you want. I don't have to finish all my slides in one day. We have 4 more days, okay? So we can go slow. Stop me if you have a question. And what I also would want is, in every half an hour, 45 minutes, after I complete a certain topic, we can have a set of discussions, and you can have, we can have a lot of interactions. You can talk among each other. You can share your experiences. So let's make this as a dialogue rather than just a monologue. If I just, and I keep telling this to my students all the time, if I have to just come, stand in the class and deliver a lecture, the best way for me is to send you a video YouTube link, right? That's best. You can sit and watch me whenever you want. The reason why we are all in one room is to make sure that we can interact and we can talk. Okay? So with that, I will start with, so the way we have organized, and it should be in your folders, that we'll do cements and hydration today as much as I can. I may have to spill over a little for tomorrow, because microstructure doesn't form without hydration, right? Cement has to hydrate for microstructure to form. Microstructure has to form for everything else to happen. So we have to talk about a little bit about cements and hydration. And if you have to talk about cements, hydration, you can't talk about hydration without talking about what's in the cement that you have that creates the microstructure. So we'll do cements and hydration. Tomorrow we'll do very early age properties in microstructure. The 3rd day we'll do, I think, mechanical properties. The 4th day we'll do characterization. The 5th day we'll do durability. That covers the entire. Okay, so we'll start with some very general structure. Very general idea of how every material is constituted. So before we look at concrete, we can think of any material that you will ever have in any sphere of activity. It goes down to the fundamental chemistry, right? You have atoms. If you don't want to believe in bosons and all of that, we can start with atoms like we studied in school. 5-10 years down the line, students will start learning from bosons and all those subatomic particles, but we'll talk about atomic particles. So there's an atomic arrangement. Now, if you look at your periodic table that you see in your chemistry class, how many atoms in a periodic table? Give me a range. Nobody can tell with certainty because things keep changing. Roughly 110, right? 110 atoms. 110 elements, which has their own atomic structure. How many materials have we formed out of these 110 elements in the world? What would be the theoretical number if one wants to guess how many materials, if you are given infinite power to make as many materials as you want from the periodic table, because you can't make from anywhere else, how many can you make? Math problem. There's an IIT entrance math problem. 110 factorial, right? Theoretically, 110 factorial. How many is 110 factorial? 110 times 109 times 108, you'll go all the way till 1. Look at the number. So theoretically, that many is possible. Now, chemistry says, oh, hold on, I cannot mix the rare earth elements with the metallic elements. I can't mix this with that. Hydrogen and helium can't mix, right? So you have a lot of constraints, but still the number of materials that we have generated is humongous. We have compounds, multiple element compounds, combination of different compounds. We have alloys, which are not compounds but solid solutions. We have so many different things.
So the structure of any material, when it comes down, you start off from the atomic scale. Oops, where's the pointer? Which one is it? The red one. Okay. Oops. What did I do? Okay. So you start from the atomic scale. Let's say that, okay, it's too complicated for me. I don't want the atomic scale. I want something that is more generic. So if you look at concrete, this is what you will see in a structure that's outside, right? Large scale structure. If you take a piece of concrete and look at it with a naked eye, that's what you will see, right? Aggregates, cement paste that's gluing all the aggregates. If you put this little bit of cement paste under a microscope, that's what you will see. But now you look at something that's looking more homogeneous, right? If I see a concrete column, concrete bridge, if you ask a kid, how many materials do you see in a concrete column? The kid would just say one. But the moment you put it down, give him a piece of concrete and say, how many materials do you see? You will say 2 or 3 depending on how good your eyesight is, right? You will see the coarse aggregates, the fine aggregate, cement paste. If you give somebody a micrograph, a picture from a microscope, how many faces are there? You will say, I don't know, depending on where you have taken that picture. So the complexity increases as you go down in scale in any material. Complexity increases as you go down, as you go smaller and smaller and smaller, complexity increases. Simple example. When I was growing up, every disease I got, my father took me to one doctor. He gave a medicine. Maybe I would have gotten cured naturally or the medicine cured. Now, there is a doctor for everything. The more we know about the system, the more complicated, the more minute it gets. Right now, there is a specialist for everything that you can think of. Very similarly, the more number of phases, the more complication that you will end up with. Okay, so for concrete, it's from the Latin word called concretus, which means just to grow. Concrete means to grow, not to grow trees on concrete, okay? To grow by itself, to change its structure by itself. It's a formable rock, it has binder and filler, all of these things you know, so we'll quickly go through it. But just to look at the scale of use. Now, it is the most used material after water, right? So no question, there's a lot of people saying, oh, concrete is not sustainable. So I'll come to the sustainability point also. Concrete is not sustainable. You will hear a lot of people saying that, right? Oh, this is not a sustainable material. True to a certain extent. I think we should accept the fact that this is not the most environmental friendly material that you can build. Now, if I want to build something, and food, clothing and shelter are the basic needs of human beings, right? So if I need something to build for people to live in, if I need something to build for me to drive through, if I need to build something to bridge over something, what are other options? If not concrete, what will you have? Give me some options. Asphalt? Asphalt only for one purpose, that is roads. And anybody who is talking about asphalt as a sustainable material should think twice, because where is it coming from? Petroleum, right? So if you think petrol and the extraction of crude oil and petroleum is sustainable, all power to you. What is the other option? Steel. Steel takes 3 times the amount of energy and 3 to 4 times the amount of CO2 emissions to make per unit mass than concrete. But why are we not complaining about steel? Very simple. Human psychology. I don't see steel being made. I see it only in the store. I see concrete being made every day. I see the dust around it. I see people from cement plants coming, dumping things. I see water being drained out from my wells. I feel it. I feel the pain. In steel, you just pay and get it. You don't feel the pain, right? Human psychology. That's why, again, anything that's sustainable, any talk about sustainability cannot, so whatever is sustainable for you may not be sustainable for me. Years ago, our ancestors lived in caves and huts. Very sustainable way of living, right? They lived in caves. There was no electricity, so there was no coal being burned. Wonderful. There was no food being processed. They eat fruits from trees. Wonderful. They pluck things off. Very sustainable way of life. They didn't make any clothes by chemical treatments. They just used leaves of trees. Can we live like that? So that was very sustainable. But sustainability has a context built in it. Sustainability depends on what is the context you're asking sustainable. If you're really sustainable, if you say that I don't care about the context, I am a very sustainable human being, stop driving your car or bike today, walk to every place. Can you do it? Stop traveling in an airplane. It's the biggest contributor to greenhouse gas emissions. Right? So we can't do all of that. So sustainability has to be context driven, whether it's concrete or any other material. With concrete, we have to be careful about the fact that we need to minimize the amount of perishable resources that we have, which we use in concrete. And we also need to be very cognizant of the emissions that we generate as a result of concrete use. And there are so many ways of doing it. But again, in a room like this, we can't make things happen. Things have to change by changing specifications, changing standards. Somebody should be confident and comfortable. Now, I can tell you what is the limit of fly ash use in India in concrete. So if I have an M40 concrete, how much fly ash am I legally allowed to use as per IS standards? 30%? 35. 35% is the legal limit. Where did the 35% number come from? Why did the 35% number come from? What do you think? Trial and error research, very good answer. Yes, that's where it started. And then, after research, what happened? Forget about that. We'll come back to the calcium hydroxide story as we go through. What else? Regulatory constraints. Why did they regulate to a certain number? With ordinary Portland cement, you can do whatever you want and that thing will hydrate and give you strength. You can add more water. Cement is such a forgiving material. It'll say, okay, you put more water, that's okay, I'll try to hydrate more and fill all the pores. Fly ash can't do that. Fly ash needs something else as a catalyst to work to help it. So the regulatory authorities came in and said, no, you can't throw in like this because you really don't know what's happening. Have you still seen the back of the guys pouring water in the back of the truck when the concrete is not very flowable? You see that now, right? When somebody says water cement ratio of 0.4, you'll make it 0.45. Has those structures failed? No, they stand. Very forgiving material. So there are regulatory reasons for us to stick to a certain number, and also it's to avoid mishaps because people do things wrongly. Concrete is a site fabricated material. Most of the time, precast construction is not very strong in India unless you are talking to L&T or a few companies like that who have precast plants and they are good at building precast structures. All of us use, and if you look at any common residential construction, like Narayanan was saying, it's still 1.53. People still mix it the way they want to. Concrete is a very forgiving material, therefore you can do the work. But if you look at the scale of concrete use, 12 billion tons every year. This is billion with a B, so million, 1,000 million is a billion. So you can do the math. Very, very highly used material. And so in addition to size, in addition to the volume, there are size scales also. And you want the Petronas stars to stand, and the Petronas star is standing because the concrete that they used has the strength to carry the load that you're imposing on it, right? Now, concrete is very, very forgiving in another way. You always hear the weak link failing theory, right? If you have a chain, it's always a weak link that fails first. In concrete, for some reason, there are only weak links. And we'll see, I'll show you when we see the microstructure. It's made completely from weak links. The microstructure is nothing but weak links. But still, you generate enough stresses to hold the whole thing together as a composite material. And then, of course, if you go down, and I'll show you more pictures as we go through of what happens. Okay, bridges are large concrete customers. Some general pictures to show the scale and size. Concrete pavements. This is the first. I mean, it looks like a mud pavement, but this is apparently the creation of the first concrete pavement in Michigan. Oops. Lot of concrete pavements being built in the U.S. Lot of interstate highways are built completely with concrete. The advantage is that it lasts for. It's expensive to start with, but it lasts for much longer time. I heard 2 or 3 years ago that the government of India was talking about doing concrete highways. I don't know where it went now. I haven't heard anything after that. It's very difficult because, again, what controls all this is not just techniques, right? There's lobby. There is people who are lobbying for their respective products, people who are lobbying for a certain respective techniques, contractors who have been doing this always wants to do it the same way. So there is a lot of other regulations, and I actually send out one complete proposal once to Ministry of Roads, Ministry of Highways, one of those, because I had a friend who is a consultant in Delhi who was meeting the Secretary of Surface Transport, and he wanted me, so I sent a whole report on surface transport, but I think it's in some dustbin in Delhi now. But that's all I can do, right? I can send a report if I ask for, but if it goes to a dustbin, I have no control because I'm not a politician. Okay, so you can have air runways made of concrete. A lot of concrete pavements are there in the US, which have been there for really long time. You're looking at 30, 40 years. Now, if you look at other structures, nuclear reactor domes, very, very critical structures, right? Can you afford to have cracks in the nuclear reactor domes? Do you want them? If you live close to them, do you want them? No. If you live in Kalpakam and you say that, yeah, the dome has a crack, forget it. No. So I recently did a project for the Department of Energy in the United States where they are in charge of all the nuclear reactor structures. How many of you are structural engineers in some form or fashion? Okay, so you will better know what I'm saying. All of you know the idea of creep, right? Creep in concrete. So these very thick reactor domes that were built, heavily reinforced. So I don't know if you have seen or known how nuclear reactors are built. They put the reactor in and then dome it around, right? Because you can't create this very heavily reinforced dome with an opening and then take the reactor. So they build it and then take it out. In the US, they have nuclear reactors that were supposed to last for 40 years or 45 years. 90% of the US nuclear reactors are now in the 60th or 70th year, which they were designed for 40 or 45 years. Now, creep. Creep is a big function of mass, right? Self-weight does a lot of things on creep. Creep is permanent deformation under the constant stress. So you have a lot of deformation happening, these thick structures. What will creep eventually do? What will high stresses and tensile stresses in concrete eventually do? Cracks, right? Cracks start to come in. Now, how would you fix a crack normally? Your director was talking about grouting, right? And then grouting causes stresses somewhere else because you're trying to fill a weak zone and that creates stresses somewhere else. So what they did was they wanted to look at this cracking and they want to relieve the creep stresses, so they had to cut out, they did a lot of finite element analysis and cut out a few parts, and then that caused massive cracking all through the dome because stress relaxation was not proper. That reactor could never be opened back again. $1.2 billion was spent. That's $1,200 million converted into crores if you want. That's a huge amount. And that reactor could not be opened because the idea of concrete creep was, after 60 years, when it was designed for 45 years, was not accounted for. And then, so they are now embarking on a program as to see how they can extend the life of nuclear reactors. Because after Fukushima happened in Japan in 2011, you remember that tsunami and the nuclear reactor damage, right? After that, no country wants to build a new nuclear reactor because you don't know what's going to happen. Therefore, Currently, what is happening is they're trying to extend the life of nuclear reactors out to another 20 years. Which means the biggest question, what will we do with creep? Right? Where does creep come from? And I'll talk to you about that when we get there. Where does creep in concrete come from? Creep comes from the microstructure of concrete. Creep comes from the layers of CSH, calcium silicate hydrate. It is a microstructural property. Where is it manifested? In the big, massive dome as cracks. You see the connection between the extreme small scale and the large scale? Right? So if you're trying to solve creep, you don't solve it by grouting. You try to solve it at the micro scale to see what is happening. There are techniques called atomistic modeling. Have you heard of atomistic modeling? Molecular dynamics? A lot of people do this on trying to see how two individual atoms interact. Very small scales. That's where all this comes from. I'll introduce you to a few of those things. I just want to give you an idea that whatever you see at such large scales are nothing but manifestations of what happens in the very small scales. So you can't just go and say, yeah, I see a crack, I fill a crack. It might work in certain occasions, but in critical structures, very unlikely to work. That's the early concrete road in Michigan, 1909. You can see by the vehicles that they were using at that time. It's really old. Energy structures. Look at the size and scale of these structures, these offshore platforms. Right? Concrete is the only material that you can use to construct those. Of course, historically, people did things with concrete. Big bridges, precast bridges. So finally, you have cement, water, fine aggregate, coarse aggregate. This is an old school. Now, no concrete is made without chemical admixtures. You have a cocktail of chemical admixtures, not just one. You have one chemical admixture for every one to reduce the water, one to use in hot climates, one to use in cold climates, one to retard, one to enhance the hydration, one to waterproof, as many as you want. And then you do all these, and what do you do? Oh, there is cement admixture incompatibility. I have a very simple example for this. You will immediately understand. You have 15 dishes spread in front of you. You indiscriminately eat all of that. What will happen? Concrete will do the same thing only.